Okay. First of all, let's define what a slope field is. Turn to your neighbor or your neighbors and discuss what you think a slope field is. You've done them before. What do you remember them being? 1, 2, 3, go.
Slope on all points, I guess.
I mean, think about it, like when you take the integral of something, you always have the plus c.
Yeah.
So, the slope field, slope field is just saying we don't know what the plus c is, so here's the general.
All right, 5-4. What'd you say?
The slope at all points.
The slope at all points. 5-2.
The general slope at a certain point, or the general slope at a certain area.
Okay, 5-5.
The graph of the slope at each point.
Okay, so you remember that we are graphing the slope at each point. Okay, basically what it is representing is a graphical solution to a differential equation. What do I mean by differential equation? A function defined by the derivative, okay? This is a differential equation, dy dx equals something, okay? So you all remembered how to do it. It's to put the slopes at each point, okay? But it's representing a lot of graphical solutions to the differential equation, okay? As Josh was saying, I was eavesdropping. When we have a differential equation, when we take an antiderivative, we have that plus c, so really we have like an infinite number of functions that could have that derivative, so the slope field is representing all of those, okay? So let's remember how we do this, okay? Oh, come on. I thought it would stay there, I guess. Well, that's good. So we're going to draw the slope field of dy dx equals x squared. Okay? How do we figure out all of our little slopes? Do you remember?
We literally plug the coordinates into the dy dx, and when we find its slope, we put the slope of whatever into it.
Okay, so we're going to evaluate the differential equation, dy dx, at all these different points. So if dy dx equals x squared, and we plug 0, 0 in for x squared, what do we get? 0. So we need a little itty-bitty tangent line with slope of 0. Okay. dy dx evaluated at 0, 1 is going to give us a slope of 0. Okay. Since this is only relying on x squared, where else do we have 0 slopes? Give me another point, Gabby, with a 0 slope. 0, 2.
Isn't it the whole?
Wait.
That's 2, 0.
Yeah, that's 2, 0.
Thank you. That's why you were looking at me funny, wasn't it? Thank you. Okay, anywhere where x is 0, we have a slope of 0. Okay. Now let's move to the actual 1, 0. What is that slope? 1. Okay, if you want to use a ruler or like your IV to make these, you can. But if you think of a slope of 1, it would need to look like that. Okay, dy dx evaluated at 1, 1. What is it? 1. Okay, and I think you guys can see that anywhere x is 1, we're going to have a slope of 1. Do we have slopes of 1 anywhere else?
Yes,
Where?
-1.
When x is -1, we're also going to have slopes of 1. How about at 2, 0? What are we going to have? Slope of 4. And anywhere x is 2, that's going to be the case. Okay. And then what about when x is -2? At all those points, we're going to have slope of
4.
4 as well. Okay, so what function does this kind of look like if we were to connect those tangent lines together? It looks like a cubic function, right? Does that make sense?
Mm-hmm.
Yes, okay. I started out with an example that we could easily think about in our head. When our derivative is x squared, our antiderivative would be a cubic function, right? 1/3 x cubed, to be exact, plus c. So I like to think of slope fields as, have you guys ever seen like those wind maps? You know, with all the little lines like telling you where the wind's blowing, right? That's kind of what this looks like, okay? If we were to like draw a particular solution, we would just use these little tangent lines like the wind blowing us, okay? All right, moving on. Okay, what I'd like you to go ahead and do is draw me the slope fields for y prime equals x plus y. Y prime is x plus y. As you draw your slopes, it should look similar to what I have up there. I would really use the fact that, you know, if we have x plus y, then we're going to have some patterns happening, right? When x and y are opposite, you're going to have 0 slopes. So those would be the easiest to put in first. Okay. And then you can kind of see a pattern emerge. Okay, use that pattern to your benefit. Now it gives us a particular solution of 0, 1. And they want us to draw the solution to the differential equation that goes to the point 0, 1. Okay, so this is where you need to let the wind blow you, let the wind take you. Okay, we can see, you see how there are 0 slopes here in this diagonal? Okay, so as we start to follow this slope, we know that we're going to need to have a minimum somewhere in there, right? Because we need that 0 slope, and then we're going to have to approach those -1 tangents, okay? And then, oops, the wind can take us there. Okay, so this is what our particular solution would look like. Okay. All right, next I want to talk about the difference between the general solutions and a slope field compared to the differentials and their slope fields. Okay, there's two different types of questions you could get as far as what's being represented on the slope field. Okay, so here I have two slope fields, and I want the equation of the general solution that it could represent. Okay, so what are we comparing if we're looking for the general solution? I think the easiest one to talk about is like number 2. Which one of these equations would be a general solution for number 2? X cubed, because that is what it looks like. Okay, our slope field is going to give us the general, a bunch of general solutions, right? So these all are going to look like y equals something. Okay. Okay, so now that we have that straightened out, what about number 1? Which one is that? That is the sine function. Okay. Go to 0, 0, and we can see that sine wave in there. Okay. All right, now probably the more difficult of the two types of questions is matching the slopes with their differential equations, okay? Remember, when we have a differential equation, we take coordinates and we plug them in, okay? So what I want you to do, you and your neighbor or neighbors, you are going to work together to match these 6 with their proper pictures. I'll give you about a minute to 2 minutes. I want to hear talking. Not totally done. you wait till we're done?
Yeah.
All right, let's talk about these. Are you guys done?
Yeah.
What? Realize I could get that.
Earlier, those are slope fields are easy.
Pod 4, give me one that matches up.
Four and B.
B is number 4. You guys agree?
Yeah.
Awesome. Okay. If we see like all of the X columns have the same slope, that's kind of what gives it away, right? Pod 2, give me one.
We got, D is number 6.
D is number 6. 6 is sine X. This looks like a negative cosine curve, right? Those should match together. Good. Pod 5, give me one.
A is 3.
A is 3. I like A. Okay. 2 minus y. When y is 2, we have 0 slopes, right? So we gave it away. Pod 4.
One is F.
1 is F. Okay. E to the X. Okay. Did you think about e to the x having a derivative of e to the x, and so that looks the same, or did you actually plug in numbers?
We just thought like more like end behavior.
Okay, good. Pod 2.
C is number 2.
C is number 2, and did you get 5 for E?
Yeah.
Okay.
How would you draw C?
Well, first off, you can't.
It depends on the solution that it gave you, right? So it gave you, if it gave you like this point, you would have to draw, like it would be a hyperbola, kind of either this way or this way, depending on which value it gave you. Okay. Now let's talk about why we have slope fields. Okay. You guys already know how to do differential equations, okay? Can we separate our variables here to take the integral, the antiderivatives? We can't, okay? Here we can like multiply the y over, multiply the dx over, and we can integrate both sides. Here we cannot. 3, we cannot, okay? So slope fields help us kind of determine what our solutions are, to where we can't do it with antiderivatives, okay? Okay. All right, here is an example of an AP question. Okay. So here we have dy dx equals xy over 2. Now, this is something that tomorrow we could separate our variables and do differential equations. We're not going to do that yet, but tomorrow we could. So go ahead and fill out that slope field for me, please. you want to check your slopes with mine as you're doing them, I have my slopes up here. Okay. Typically on the AP exam, you get 1 point for your zero slopes and 1 point for the other slopes. Okay, so they would check to see if along the axes you have zero slopes and everywhere else do the slopes match up. Okay, now in part B, write an equation for the tangent line through 1, 1, and then use your tangent line to estimate the value of 1.2. Okay, Sammy, what's the slope of our tangent line at 1, 1? 1/2. So we have y minus 1 equals 1/2 times x minus 1. That is our tangent line. Okay? We use tangent lines to approximate values on the curve. Okay? We could, work backwards and we can find this particular solution that goes through 1, 1. Not always is that a possibility. Okay? So sometimes we have to use the tangent line to approximate a value on the curve. So let's approximate 1.2 using our tangent line. Okay. When x is 1.2, what is our y value?
Y would be equal to 1.1.
1.1. We get 0.2 times 1/2 is 0.1. We add the 1 over. Now, if we were to actually find the real value of f of 1.2, would this be an over or an under approximation? Bailey, why?
Because it's exponentially increasing. Slopes are, it's not just linear.
Okay, let's think of a better way to say that, because technically this is an exponential. Because it's concave up. When we have a curve that is concave up, our tangent line sits underneath. Okay, so like if we were to draw this curve, right, our tangent line would be sitting underneath. If we had concave down, it would be an over approximation. Okay. What's nice about slope fields is you don't have to actually find the second derivative. We could, okay, but since we have the slope field, we can tell that our curve is concave up where our point is, and so we know that our tangent line is sitting underneath. If we didn't have this picture, we would actually have to find the second derivative, plug in our point, and see if it was concave up or concave down. Okay, so thank you, slope fields. All right, now, the further away we get from our coordinates, the less accurate tangent lines are. Do you agree? Okay. Is there a way to be more accurate than a tangent line? Yes, yes, there is. Euler's method. Okay?
Looks like Euler's.
Yes, his name is Euler. I like to call him Euler, but he's really Euler. Okay? Euler's method. We know Euler. We have E, the number E, because of Mr. Euler, right? He also invented this method. Okay, so not all differential equations can be solved. So, we have slope fields that can be general solutions, but, they're giving us the trends, okay? They're giving us a general idea of what's going on, but it's hard to be really exact with where our values are. So Euler's method basically, instead of having a tangent line approximation, okay, Euler's method evaluates a tangent line and then moves a little bit along that tangent line and then reevaluates the tangent line and moves a little bit further and then reevaluates the tangent line and then moves a little bit further and reevaluates the tangent line to get a better idea of where we are. Okay, if you can compare that to just a normal tangent line, okay, if this was like x is 1.2 like we did on the earlier example, okay, if we keep reevaluating our tangent line, we're going to be closer to the curve than if we just have one tangent line. Okay, so that's what Euler's method is going to do. It's going to be more accurate than just the tangent line equation. Okay, but it is going to take some calculations after calculations after calculations. So you will need your calculator. Okay, and this is what we're going to do. We're going to start with a point, and then we're going to evaluate our slope, just like we would for a tangent line. Okay, now, we know that slope means change in y over change in x. Okay, so they're going to tell you, or I'm going to tell you, or you're going to decide, but really somebody's going to tell you how many steps to take. And just like we did kind of with Riemann sums, we're going to have that change in x. So if we're going from 0 to 1, and I tell you to take 4 steps, each step is 0.25. Okay? And that is like our change in x. All right? So slope is change in y over change in x, which means change in y is slope times change in x. So once you evaluate your slope, you're going to take that slope times your change in x, and that's going to give you our change in y, which we can add to our original y value. Okay, and so then we're at a new coordinate. Okay, we are going to repeat this chart until we've taken the number of steps that we needed to. Whatever your y value is here, if it's not our last step, we're going to fill out the next row of the chart. Okay, so if a is like 0 and our step is 0.25, then your x values are going to increase like so. Like that. All right, so let's look at an example. You're excited? I'm excited. Okay, so I want an approximation for 0.8 using Euler's method with 2 steps. And I'm giving you an initial condition of 0, 5. Okay, so we know we're going to take 2 steps, which means our change in x, we need to take where we're stopping minus where we're starting over the number of steps. B over 2 minus n. B minus a over n, just like we did with Riemann sums. So our steps are 0.4. Okay. Okay, so we are starting out with the coordinate 0, 5. What is the slope at 0, 5? -2. Thank you. You just plug your point into your differential equation. Now, our change in y, remember this equals our slope times change in x. So you're going to take your slope times your change in x. What is that? Negative. We're taking our slope times our change in x. as we travel along this tangent line, our y value is now going to be 5 plus negative 0.8, which is 4.2. So now we are at the coordinate 0.4, 4.2. And now we're going to,
About 0.4, which is change in x, not your x.
well, our change in x. So every time we go to a new row, we're adding our change in x.
Oh, I see.
Okay? So now we're at 0.4, 4.2. And instead of traveling along that same tangent line, we're going to reevaluate our slope. Okay? So when we plug 0.4, 4.2 into our differential equation, what is our new slope? 1.6. Okay? Now, we need change in y, which means we take this slope and multiply it by our change in x. So negative 1.6 times 0.4. Which is?
.64.
Negative 0.64. That's our change in y. So we take our y of 4.2, we add the negative 0.64, so our new y is 3.56. So now at 0.8, our y value is 3.56. What's the key to being more accurate?
Smaller steps.
Smaller steps. So if we were going from 0 to 0.8, we'd have smaller steps and there'd be more of them, right? The more steps you take, the more accurate you're going to be to what the real coordinate is.
So in other words, the limit as n approaches infinity. In other words, if you take the limit as n approaches infinity, plug in the equation, and you get the exact thing.
Well, we don't actually know what the exact value is because, well, here we could, but most of the time we're going to use these on solutions that we can't, differential equations that we can't solve using antiderivatives.
Okay.
Does that make sense? Okay. Okay. Now, could we solve this one using antiderivatives? Could we, this is what we're going to do tomorrow, right? We could multiply that dx over and integrate both sides, right? So y is 1/2 x squared minus 2x plus c. Okay, and we could, okay, since our initial condition is 0, 5, y is 1/2 x squared minus 2x plus 5. If we were to evaluate this at 1.2, the actual value of our function at 1.2, excuse me, not 1.2, but you guys let me write that. It's at 0.8. Our actual value of f of 0.8 is 3.72. So we're pretty close, okay? If we would have taken more steps, we would have been closer. I think kind of
like so more number of steps is like the more steps you take, the more accurate you'll be. Is there a way, or is there a method or an equation where you could take n n as the limit as n approaches infinity, like have it make infinitely many steps, just like the limit. Is there an equation or method to do all this and make it into a short equation like we did with the Riemann sums?
I'm not sure, because with Riemann sums, all of our heights were like the same. You know what I mean? Here, our y value keeps changing, so I'm not sure. We can look it up later. Okay, it's a good idea. I have not seen that, because it's not out there. So let's keep that in the back of our minds, okay? All right, you have your calculators ready? dy dx is 2x minus y. This is one where we cannot separate those variables, okay? So we don't have a way right now of finding what this equation is. So the only way we can approximate is with tangent lines. Euler's method is going to give us a better approximation. So we have the initial condition, f of 2 equals 3. And we want to approximate when x is 1.5 using 5 equal steps. Okay? So our change in x is, well, no, it's 1.5 minus 2 over 5. Okay? You need to take b minus a, where you're ending minus where you're starting, over 5. Okay. Okay, now, we only have like 7 minutes left in class, so your participation would be helpful. So when I ask you to calculate something, I need you to do it and I need you to answer me, okay? Otherwise, we're never going to get out of here. So we begin at 2, negative 3. dy dx is 2x minus y. What is our slope?
It's 4.
1.
Oh, well. Okay, I got the back.
I don't know if it means there. Okay. Which means our change in y is that slope times our change in x, so negative 0.1. That's nice. We started with a y value of 3. We add our change in y. We are now at 2.9. So now our coordinate is 1.9, 2.9. How did I get 1.9? I added delta x. Good. Okay. So now let's determine our slope. X is 1.9. Y is 2.9. What's our slope? Say louder. 0.9. Multiply that by delta x. We get negative 0.09. Thank you. Which means our new y value, we're going to add that to 2.9, so we're at 2.81. Okay. So now we're at 1.8, 2.81. What's our new slope? Great. Multiply our slope times delta x to get delta y. It's a nice multiplication, right? So what's our new y value? We take our y, add delta y to get okay, we're almost there. We are now at 1.7, 2.731. Please calculate our slope using that coordinate.
0.669.
0.669. We take our slope times delta x to get negative 0.0669. And our new y value is
2.664.
all right. Last time. Our new x is now 1.9 with our y value of 2.6641.
Wait, 1.9.
Yeah. I added. There we go. What's our new slope?
0.5359.
Thank you. Which means when we take slope times delta x, we have negative 0.05359. Add that to our old y, so our new y is 2.61051. Okay, so that means, okay, we could make, I don't have enough room and I can't scroll up. But what's happening is when x is 1.5, our y value is 2.61051. I will tell you that if we use the tangent line at 2, 3, we would have gotten 2.5 as our answer. That's a big difference, 2.5 to 2.61. Okay, I mean not a huge difference, but enough of a difference. Okay, we get a lot closer. Are there any questions?